All right, let's get started. Good morning. Any questions before we start? Okay, so today we are going to go in, open up a simple neural network, see what goes on inside all the wiring, and then we're going to see how to do learning for a simple neural network. And we are going to understand that in a way so that then you can apply it even for more elaborate networks. So not just a network which has one hidden layer, but which potentially has more than one hidden layers, right? So the idea is still the same. So that's why I'm going to go through it in a way so that you can understand it in a very general way, right? However, what you will see is that the assignment 1 description, right, all the 8 pages, also has that derivation in pretty good detail, but that is focused only on that architecture, one hidden layer, one output layer, and inputs coming in, right? So if you want to do the assignment, you can sort of follow that reasoning. But if you want to just understand it in a more general way, let's do it the way I'm going to do it today. Both of them will give you the same answer. So they are the same. It's just how we do the notations. All right. What you will see quickly here is that the only issue with training in neural networks is the notation. You get lost in the whole notation and all different types of neural units we have and so on. So I'll try to be very careful in how we define different terms. And if you see any discrepancy, just shout it out. There will definitely be some errors that I'll make, but I'll try to be as careful as possible. Okay, so let's get started. So just to review, this is the neural network that we will be looking at. I changed it a little bit from last time because I got a sense that the intercept was throwing some of you off, right? So here's an example, right? So this is called a multi-layer perceptron because it has these units which are kind of very similar to perceptron unit. Of course, they have this sigmoid thing at the end, but otherwise they're very much like perceptrons. So you add all of them together, and we saw how to do that last time, right? So the idea is that you have some inputs coming in, they go through this hidden layer, and they go to the output, and then so on, right? So when you're testing, so let's assume that you already have learned this network. So what does it mean to learn a neural network? Is that you know all the weights that are inside these units, right? So let's say you know all the weights. Then if you want to make a prediction, so what you do is you get your new data point. Now your new data point will be defined using, in this example, 5 features, well actually 4 features, x1, x2, x3, x4, and then we add an intercept term as well, 1. So you make a vector like that, right? Then you push it into this network. So the first thing what happens is that all inputs go to all hidden units, right? Then inside the hidden unit, these inputs that are coming in get combined using a weight function. So you do this, so you'll have 5 weights in this hidden unit. They'll get an inner product with these 5 inputs. Then you add them up. Then you apply the sigmoid function, and that comes out as an output of this hidden unit, right? Now that output goes to all of your output units. Okay, so it looks very much, I mean, all the units are the same, right? Last time I gave you an example. So you can build the whole neural network using the same unit. And then at the output, what happens is that each output unit corresponds to one of your classes that you want to predict. And it takes in all the inputs, including a bias term, adds it up, right? So even here you will have six weights in each unit, which will get multiplied with these 6 inputs coming in, and then you produce one output. All right, and then at the end, what happens is that all of these outputs will be between 0 and 1 because they're output of a sigmoid unit, right? Then you pretty much see which one is the highest, and then you say that is my class, right? So ideally, if the input belonged to class number 1, then the output should be such that this value would be 1 and all of this would be 0. That's the ideal case, right? Typically it won't happen that way, but the idea is that you want so then the training becomes that you want to set the weights such that you get that kind of behavior, that if you put in an instance of class 1, then the output at this end should be that O1 should be 1 and everything else should be 0, or at least O1 should be high and everything else should be low. So that is how the prediction works. So that's what we call the feed forward propagation. So you take your input and you sort of pass it through this, right? So in general, if you add more hidden layers, the process would still be the same, right? Because every unit is exactly this. I mean, conceptually, it's the same thing. There is some input coming in, it's getting combined inside, transformed non-linearly using a sigmoid function, and then passed on in the front, right? So it just goes on like that. All right, any questions so far? All right, okay. Don't want to talk about this. And then we also talked about the threshold unit, right? So the idea is that that unit needs to do a nonlinear transformation. We choose this as our unit, right? This is sigmoid. So whatever goes inside sigmoid, it is 1 over 1 plus e power minus of that. And it provides a nice sort of a nonlinear term, right? So here is why we use sigmoid as a unit, okay? And not, so there are some other options. So we could have used the linear unit. Remember, the perceptron, the unthresholded perceptron is what we call the linear unit. All it does is it does W transpose X, right? And nothing to it, right? So whatever comes in comes out just like that. So that would look like this. If you do a thresholded perceptron, then it would basically put a threshold to that, and it will turn it into a step function, right? The reason we use sigmoid is because it has this nice smooth nonlinear shape, right? Which is easy to work with. When we compute gradient later on, you will see that because of this sigmoid unit, you can compute very nice gradient. However, if your unit was like this, then it won't be easy, right? Even this also is, we could use this, but then this would not give us a non-linear effect, right? This is just taking in whatever is coming in and just dumping it out. So that is the reason we do sigmoid. In the end of the class, I'll talk about a few more types of functions that we can use. In fact, one of the most popular functions right now is what we call regulated linear unit. So it actually looks like this, except that it does this piecewise. So if it is less than 0, if your x is less than 0, then it is just 0. So it acts like this. So it is not non-linear as such, but it is also not just linear, right? So it works pretty well. But for this class, we are going to assume this is our activation unit, all right? All right. So this is the architecture of our feed-forward neural network, right? So now what we want to do today is see how can we learn the weights, right? So remember, there are weights inside each one of these units, which we don't know what they are. So those are what we call the parameters of our neural network, right? There are some other things that we need to specify as well. For example, we need to tell how many units there should be here, right? And in general, we need to also tell how many layers we want, and in each layer how many units we want, right? Those kind of parameters are something that we will specify beforehand, right? So that's why we call them hyperparameters. So those are our hyperparameters. That are not automatically learned from training data. They are sort of estimated by doing this cross validation that you will be doing for the assignment as well. But the parameters that we learn using all of this gradient descent is what we call the parameters, right? So let's see what our parameters are. So I'm going to introduce some notation here, right? Or some terms here. So we are going to assume that our data object is represented using D features, right? So overall, there will be D plus 1 input nodes because there's one node for the intercept. So in this case, D is 4. So there will be 5 input nodes. There will be, and we assume there are M hidden nodes. Okay, so M is the number of hidden units in your network, which does not include this one. See, this is just an intercept. There are no weights inside. The effect of this unit, it just sends 1 out, right? So we're going to ignore that. So in this network, M is 5. Okay, so they have 5 hidden units, and then you have K output nodes. So K is 4 in this case. K is determined by how many classes you have. So that's you don't have to really think about it. If you are trying to learn 10 classes, your K will be 10. And D is of course specified by how many features you have. So that's fine as well. The only thing that is not specified is M, and that's where we have to just specify whatever we want to, right? So M is sort of this free parameter, hyperparameter that we are going to assume that we know, all right? So now let's look at hidden nodes, right? So each hidden node, I'm going to denote hidden nodes by the subscript j, okay? So at each hidden node, there's a vector which we call wj, right? Wj will have d plus 1 entries because the effect of wj, so wj is, for example, this will be w1, right? That w1 vector needs to combine all of these inputs, right? So it will have d plus 1 length, right? So there will be m vectors like that. Each vector will have d plus 1 length. And at output nodes, you will have vectors which we denote as wl. L will go from 1 through k, right? Because there are k output nodes. And that vector will have m plus 1 entries, right? The length of that vector will be m plus 1 because it needs to combine the stuff coming in from the hidden units, right? So there are m hidden units and there is one bias node. So they will all send in m plus 1 wires coming in. So you need m plus 1 length vector here to combine, okay? So that is the thing. So these are the things that we need to learn, right? We need to learn all of these vectors. Wj's, where j goes from 1 through m, and wl's, where l goes from 1 through k. So these are our parameters, all right? In the case of perceptron, if you remember, we just had one weight vector. Now we have lots of weight vectors, okay? In the assignment, for notational efficiency, and also when you implement it, we tend to stick all of these hidden node because all of these vectors will be of same length. So we just stick them into a matrix, a big W matrix, and same thing here. It's easy to sort of work with them that way. But for understanding today, we're going to assume that we have all these vectors, right? And we just need to figure out what they are, okay? So the process of learning is very similar to perceptron learning. You assume some initial values for all of these weight vectors, okay? Then you take your data and it goes forward, and then you compute your objective function based on what you found output and the actual true labels. You compute your objective function, then you compute the gradient of that objective function with respect to each one of these weights, right? In fact, you want to compute the gradient with respect to each element inside each weight, right? So you have to compute a whole bunch of gradients. And once you compute those gradients, then you can do your gradient descent and figure out what is the best value, right? So that is a general strategy. The only tricky part here is computing the gradient is not straightforward because of this architecture, all right? So let's look at that a little bit more. Any questions so far? Okay. So here I already drew something. Oh, I used a pencil. Maybe I'll. Looks really ugly here. Okay. Well, okay. So, let's go with it. So this is kind of like what we had there as well, right? Our neural network, right? I changed some things, right? So the first thing I changed was that, remember, you will not only have one training example, you'll have n training examples, right? So the training examples, I'm going to denote them by this subscript I. So this vector x of I is my ith training example, okay? Which means that my so this value xi1 is the first feature value in my ith training example, right? Because you'll have I of those, yeah? So the idea is that you pass each training example one at a time. So for one training example, you start from here and you reach up to here, and then you compute the error, the objective function with respect to that training example, and then you sum them up, right? Because and I'll come to the loss function, but the loss function or the objective function that we want to minimize is just an aggregate of all training examples. So even if you work with only one training example, at the end you just need to sum them up. So that's why it's sort of not that important to worry about the summation. That's just a simple summation, right? So these are the inputs for the ith training example, right? So xi1, xi2, xi3, xi4, and 1. they all go to these hidden units, right? Now in the hidden units, what I have done is to differentiate between the hidden units or hidden layer and to differentiate between the units on the hidden layer and the units on the output layer, I have indicated these units as W1, and I've put a superscript 1. 1 means it's in the hidden layer, okay? So there will be 4 hidden units, of course, and then there's a thing here, the bias term. Okay, so what these will do is they'll take all of these inputs, compute the W transpose X, and then they'll compute the the sigmoid transformation, pass it on here. Now these are our output units. You'll have 3 of those because you have 3 classes in this example, and then I denote them by this 2 on the top to differentiate between the from here, right? And then what they do is they take the inputs, they compute these outputs, right? So you will get 3 output values, okay? Now we need to compute the loss, right? The loss that we incurred by this prediction. So on this side, so these are my outputs. Sorry. So these are my outputs. And these are my true, this is my true label. Now this is one part that you have to be a little careful about, right? So remember, in our training data, right? Our training data will look like this. We'll have an example xi, which is a vector, which is our all the features. So this will be in, of course, r to the d. Oh, here it is. And on this, and corresponding to that, we will have a yi, right? Yi will be the true label. Now, when it is given to you, yi will just be a categorical value because these are classes, right? So yi will belong to 1 through k, one value between 1 and k, right? Because if it is class number 4, then yi will be 4 and so on. But we want to compute, we want to compare that yi with these outputs, right? So what we do is we convert this. We do what is called 1 of k encoding and convert all of these categorical values into a vector of length k, okay? And what we do is that if yi, whichever value yi belongs to, let's say yi was 5, so we will set the 5th value to 1 and everything else will be 0. Okay, so we just convert it into a vector. All right, any questions about that? That's called 1 of k encoding, and I'll tell you why we need to do that, right? The reason we need to do that is now our true label will look like this, right? And then we can compare it with our outputs, because the outputs that we're getting k outputs, and the true label actually just was one value, so we converted it into 1 of k encoding. But there's nothing really nefarious going on here. All we did was that whatever the value, whatever the true class was, we will set that to 1 and everything else will be 0. Okay, so that's the only thing we did. Was there a hand there? Oh, you got it? Okay, all right. So let's say this particular for this example, let's say yi was 2, let's say belong to class 2, right? Then this vector will just be 0 1 0. The second value will be 1. If it belong to class 3, it will be 0 0 1. Okay, so that's the only thing. Any questions? Okay, so now we can compute the loss, right? So the loss would just be comparing these, right? So loss for ith example, okay, I'm going to denote it by j of I, is equal to y first, right? Okay, so yi1 minus oi1 square plus yi2 minus oi2 square, and so on until, because there are k values, right? So with the yik oik square, and we put a half in the front. Later on we'll do the differentiation, so this will help us, and compactly we can write it as just summation. I'm going to use L is equal to 1 through K yik minus oik square. So this is the loss for the ith training example. Any questions so far? This is exactly like the perceptron loss as well, right? The squared loss. We call it the squared loss because we're just doing a square. We can change this. In fact, for assignment 1, you'll see that we don't use this loss. We use a slightly different loss. It's called cross entropy loss. But the idea is whatever the loss is, it needs to take y and o and combine them somehow. Okay? So when you do the assignment, don't use this as the loss, right? Because what will change is that when you compute the gradient needs to be with respect to that loss function, right? But you will see that things don't change too much, only a little bit. All right. So now total loss for the whole training data, of course, we write it as J, will just be a summation because we have n training examples. 2 summations over here. Okay. So this is our objective function or loss function. And now what we want to do is we want to optimize your weights to compute the to get the minimum loss, right? Doing gradient descent. Now one thing you will see is that the weights are all here, right? They're all hidden inside, but there is no weight here, right? So how do you compute the gradient of this J with respect to the weights? But what you want to carefully examine is that these values, right, which are obtained over here, they are functions of all of these weights, right? So you can compute, and that's what we will do, how to compute the gradient with respect to each weight entry. Any questions so far? Yes, go ahead. Uh, are you talking about the loss? Must have made a mistake somewhere. You're talking here? Is he here? Oh, sorry. I'm sorry. Yeah, you're right. YL, right? L. Yeah. Right. Here, yeah. Oh, I'm sorry. Yeah, you're right. No, that's good. That's good. Yeah. The main thing in all of this is just a notation, right? So it's you're just computing the loss. Any other question? All right. So now let's see how to compute the gradient of this J function with respect to every weight entry that we have. Every weight that is in every vector in this whole architecture, we need to compute the gradient, all right? Because then we use it for gradient descent. So let's leave this here. We'll probably need it again. All right, so now let's see how to compute the gradient. How to compute gradient. Okay, so this is the part where I'm going to make a quick simplification, just because I don't want to write too many subscripts. Right. So the idea is that once you compute the gradient, then you can feed it into the gradient descent algorithm. So let me just, for the sake of completion, right. So this is our loss function that we wrote, right? And then what we're going to do is we are going to learn these weights by doing this gradient descent, and we are going to do it. So that gradient descent algorithm is actually called backpropagation in this context, because it's not a straightforward gradient descent, right? As I showed you, the things in the loss function do not explicitly contain the weight values, right? So we'll need to figure out how to find the relationship between each weight and the loss function, and then compute the gradient. So we do that by something called propagation of error. So we compute the error over here, we propagate it back through the layers, and then we compute the gradient at every layer. So this is general. This could be applied to any number of hidden layers as well. Okay. The gradient descent idea is simple. You understand that, right? You compute the gradient of j with respect to each one of your functions. Now, one thing you will see is that because your loss function j is just a summation of these ji's, right? So your gradient will also be a summation of these ji's. So as long as we know how to compute gradient with respect to one training example, you can then just sum it up over all training examples. So later on, I'll assume that I only have one training example and do all the analysis with that. But what you need to make sure is that when you implement it, you have to compute that gradient for each training example and then sum it up. Okay. So this I already talked about, right? So every weight entry will get updated based on the gradient, right? And the gradient will be with respect to each one of these weight vectors, and then within each weight vector it will be with respect to each entry inside the weight vector. Okay. All right. So now let's look at a hidden unit. So what happens in a hidden unit, right? So this is where I'm going to move away from our assignment description. We are going to assume a general sigmoid unit, okay? And we are going to understand what happens in a general sigmoid unit. The idea is that this sigmoid unit, right, will be either in the hidden layer or in the output layer, okay? And you have this error function which will always be at the end, right? So we need to understand how each weight entry, each one of these weights are related to that loss function at the end. It doesn't matter if it's in the hidden or output layer, the idea will be the same. So let's assume that this is a general sigmoid unit R, number R, okay? So WR. Now this could be anywhere, in the hidden or input, we don't care. It gets some inputs, okay? We are going to denote them by UR1 through whatever, right? So it is getting some inputs. It has some weights here. Those weights get combined with the input, they get added up. Then you compute what is called net of R, just a notation. That's the summation. And then that gets combined up, the sigmoid function is applied to that to produce what we call O of R. So O of R will just be the sigmoid of that net of R, right? So now let's see, and now on this side I have the loss function. I want to see, can I compute the partial derivative of this loss function with respect to any of these weight entries, right? Because that's what I need to compute the whole gradient, right? Remember, the whole gradient is nothing but the partial derivative of this loss function with respect to each one of these weight entries, right? So inside each weight vector, there are a bunch of weight elements. So I actually need to compute the partial derivative with respect to each one of these weight values. So each one of these. So we have really sort of zoomed in into the finest atomic level of this neural unit, and we want to see how to compute that. Once we do that, then it is pretty easy, right? Then once we know how to do that, then we can update it using our gradient descent rule. So that is fine. Any questions so far? All right. So now let's look at how to do that, okay? So the first assumption, as I said, I'll make is that let's assume that we only have one training example. That means I'm going to get rid of those summations, because those are just summations. So we don't really worry about it. As long as we can compute the partial derivative of your one of these entries, right, then we can just sum them up like this. So it's not that much of an issue. So I'm going to assume that we have only one training example. So we are going to drop the subscript I from here on, okay? So let's consider any weight value, not a vector, the weight value. So this is WRQ, one of these. Let's take one of these, and let's see how is that connected to our loss function, okay? So obviously, so you have weight RQ, and then URQ is the input that is coming in, and OR is the output that is going out, right? That is here. So this is, let's say this is WRQ, then URQ is the input that gets multiplied with this one, and then they all get combined to net R and then go to OR. So that's how the forward process works. So the first observation that I want you to understand is that if you look at J, right, J at the end, it will be connected to your weight through net, right? So because net is a function of WRQ, and then net goes into OR, and then OR gets combined into the J, right? So if you want to compute if you want to compute the derivative of this J with respect to this weight, you can compute it using this product rule, right? So compute it with respect to net of R, then compute net of R with respect to R of Q. And let's see why that helps. Please stop me if anything is not clear, right? So we are trying to compute the gradient of J with respect to any arbitrary weight entry in any unit, like RQ. And what I say is that this will be nothing but net of, with respect to the net of R times net of R with respect to WRQ, right? That's just product rule. Then we know that net of R, remember net of R is nothing but summation over so Q equal to 1 through whatever number of units there are in this, or whatever number of weight entries there are, U of RQ times W of RQ, right? That's the net of R, that's a summation, right? Which means that if I compute, so all I do is I open this summation, only one of these entries will depend on WRQ, everything else will have some other Q, right? So that means that this will be just U of RQ. That's the first thing, very easy, right? So now, which means that the partial derivative of this will be dj net of R times U of RQ. Now we know, now we don't know if this RQ is in hidden layer or output layer, but this is true for anything, right? It's just that this will change. For a hidden layer, this will just be the input coming into a hidden unit, and for output layer, it will be the input coming into the output unit. All right, easy. All right, let's move forward. So the next observation I want you to make is that if we consider output node, so far we were looking at a general node, but now we'll do output first and then hidden later. So let's say we are talking about an output node, right? So the net of L for an output node is connected to J only through the output value of the node, right? So if you remember, oh, let's go back here. I'm sorry. Here, right? So this is net of R. We want to compute its derivative with respect. We want to compute the derivative of J with respect to this. That is connected to J through OR, right? That's the output. So that's a second observation. So essentially, what we say because of this observation is that for an output unit, right? So output unit means, let's call that vector W of L, right? Right. So for an output unit in which the weight vector is W of L, dj of d net of L. So now instead of R, I'm going to use L because L is for output units, right? So R becomes L. So this will be equal to dj with respect to O of L, the output coming out of the Lth output unit, and d of O of L net of L. All right. So now we compute these two things separately, right? Now remember that what is this part? So J is nothing but summation over L equal to 1 through K YL minus OL square, half of that, right? I'm assuming that I'm dropping I here. Implies that if I compute it with respect to O of L, then O of L will only be in one of the terms in that whole summation, right? So everything else will disappear. So that will be half 2 times YL minus OL minus, just a minus term in the front. So that's just minus YL minus OL, right? So that's just a simple differentiation. Right. Any questions so far? That's pretty straightforward. So that means we have computed this part, right? So now let's look at this part. So this is this. Now let's look at this one. So what is d O of L net of L, right? So remember that recall that net of L is nothing but O of L is nothing but sigmoid net of L, right? Because that's a sigmoid activation, right? Implies that O of L is 1 over 1 plus e power minus net of L. Yeah? Implies that, okay. Okay, we're going to do a sort of an interesting study of the sigmoid function separately, and then I'm going to use that result here. Okay, so don't get alarmed. So let's say you have any function, right? So let's say you have a function sigmoid of z is 1 over 1 plus e power minus z, right? So what will be d by dz of sigmoid of z, right? So that will be just minus 1 over 1 plus e power minus z times e power minus z minus, right? Because you first do with respect to this, and that is this part, and then you differentiate this part, that will just be minus e power z, right? No questions here, I'm assuming. So this will be e power minus z over 1 plus e power minus z, right? Which can be written as 1 plus e power minus z minus 1 over 1 plus e power minus z, which can be written as 1 minus 1 over 1 plus e power minus z, right? Which is, now this is actually sigmoid of z, so this is 1 minus sigmoid of z, right? So the derivative of sigmoid of z is just 1 minus sigmoid of z. That's no, something I missed something. Oh, I'm sorry. This here, right? This needs to be this. I'm sorry. Okay. So this is this. This will be square of this part, right? Okay. Right. You're right. So let me rewrite it here. So it is e power minus z 1 plus e power minus z whole square, right? Good. So and this will, I can write it as right? That I've confused myself. But the idea is that at the end of it you will get this. I don't know how. Call it magic. But you can work it out. I don't want to work it out right now. But yeah, I mean it's fairly easy. You just need to rearrange the terms, right? Just like I was trying to do here, except that you just do that. But this is the result that I'm going to use, which is that if you want to compute the derivative of the sigmoid, it is nothing but the sigmoid times 1 minus sigmoid. Okay, and that's the beauty of the sigmoid function. That makes things a little easier to work with. All right, where was I? Recall that this is this right here. Okay, so let's move on to this part. So this means that since OL is nothing but sigmoid of net of L, which implies that DOL over D net of L is just OL times 1 minus OL, because OL is sigmoid of net of L, right? So this is a result that is coming from here. So don't think of it as magic. I mean, try to work it out. Maybe next time I'll come and just do it. But it works out. Okay. So this is one more result that we got. That means that now we have everything, right? So we have this thing. We already had this part, which is, I'm going to call it first result, and this is second result, right? Implies that if I want to compute dj over d net of L, I'm just going to combine the two, and it becomes OL 1 minus OL YL minus OL minus. So that's the first thing that we get. All right. And what I'm going to do is, I'm say let delta L is equal to OL 1 minus OL YL minus. I'm just going to, I don't want to write the whole term over and over again because this will come later as well. I'm just going to denote this whole term as delta L, which means that the partial derivative with respect to net of L is nothing but minus delta L, right? That is just a notational rearrangement. Now we use this result along with this general result that we had earlier, right? Which means that now we can say that the derivative of J with respect to any output node, right? So any L, any element inside an output node, so L of J is this, so it is minus delta L times U Lj. We are off the screen, okay. So you couldn't see all the magic here. Sorry. All right, here we are, right? So I just used all the results that we had so far, and then we said for any entry in a weight vector of a output unit. So for any entry in an output unit, the derivative of this is basically this. Okay? And the question is, what is ULJ, right? What is that input that is coming in, right? So ULJ is nothing but the input that is coming from the from the hidden layer. So remember this architecture, right? So we are trying to compute the partial derivative of this J, whatever we computed, with respect to a weight entry in one of these weight vectors, okay? And that is given by the delta L that we computed here times the input that is coming in from that corresponding J. So remember, there are a bunch of entries here, right? Can you see that? Yeah. And now let's say I'm trying to compute the partial derivative of this weight entry or the partial derivative of J with respect to this weight entry. So that will be whatever delta L that we computed times the input that is coming from the corresponding second entry, right? Because there's a second here. So from the second one that is coming in here. So we have all of those values, right? Because in the feed forward part, when we computed all these errors, right, we would have done all of this. We would have gone from here and we would have computed all of these things, all of these current values along these wires, which means that we know this value. So that means that now we can compute the partial derivative. So we have done half of the thing already. We have computed. So this is what is ULJ? Output of the jth hidden unit, because that is what comes to the every output unit. So now we know how to compute the partial derivative of J with respect to every element in any weight vector inside the output unit. All right. Now we have to look at for a hidden unit. Let's say we have a hidden unit and we are going to use the subscript J for that one. So Wj is the vector, is the weight vector at the jth hidden unit. So within that jth weight vector, what will be the partial? What is in that weight vector J of the pth element inside that J vector, right? Because this weight vector will have d plus 1 elements inside. So we have to compute the partial derivative with respect to each one of them. So what is this? That's what we're going to see. What is the time? Okay. Any questions so far? It's fun, right? All right. So let me switch back here. We have to make one more observation here. So this is the update rule, right? So we know this. We did. So now we say observation 3. All right. So net j for a hidden node, right? Remember that we have made this general observation here that the partial derivative with respect to any element in any weight vector will be whatever is the input times this. So now we have to figure out what is the partial derivative of j with respect to the net that is going out. So the observation is that the net j for a hidden node, right, is connected to the eventual loss through all the output nodes, right? Remember that when we do this, and that is what the whole trick, the issue is, that each one of these weight elements inside, right, they contribute to the net of j, right, whatever is coming here. Then that net of j becomes O of j, and that O of j then goes to all of these output units, right? And then that goes into all of the final outputs. That means that that net of j is connected to the final j through all of these weights, and that is what we need to be a little careful about. So the idea is that if you want to compute the partial derivative of your j with respect to any net of j inside, right, so that will be actually a summation over all output units, because it relates to all output units, right? So you basically just write it like this. It's a summation with respect to all of these output units. So we compute the partial derivative of j with respect to all of the net of L in the output units, and then we connect the net of L at the output units to the net of j here, and that's it, right? So we need to jump into that and figure that out. So I'm going to take maybe 10 minutes in next class to derive that. I mean, I know I don't have to really do it, but I think by doing this whole exercise, it becomes a little clear to everyone that, or it should become clear to everyone how this process works. So in future, if you come up with your own neural network or any other algorithm, right, so you don't have to be really intimidated by what's going to go inside, right? All you need to figure out is how are your weight parameters connected to your loss function, right? And then if you can compute the gradient, that's it. Feed it to a gradient descent algorithm and you learn your weight. So that's your training. All right, any questions? So next class I'm going to finish this discussion and then we'll move on to the next topic. Okay, all right, thank you very much, and I'll see you on Friday.